In this paper, we propose SpectralNeRF, an end-to-end neural radiance field-based architecture for high-quality physically based rendering from a novel spectral perspective. Spectral rendering is a fundamental problem in computer graphics, which can understand the absorption, reflection, and other interactions with objects and has been used to generate photorealistic images. Conventional spectral rendering involves two transformations. First, from the spectral power distribution L to the XYZ image, achieved by using integral operation through the visible light. Second, the XYZ image to the RGB image, realized by the conversion matrix. Based on the transformations of L to XYZ to RGB, physically based spectral rendering has been widely researched over the past decades, including stochastic sampling over the visible light, representing spectral information using Fourier coefficients, sampling in the spatial domain, and so on. However, these methods are designed for canonical ray tracing rendering pipelines, which might be time-consuming when rendering scenes with complicated geometry. Such methods predict photorealistic rendering that no effect that contributes to the interaction of light with the scene is neglected. However, they merely generate one image of the current viewpoint and are limited in representing the scene. Recently, Neural Radiance Field (NeRF) is designed to render compelling images of 3D scenes from novel viewpoints. Previous methods represent a 3D scene with explicit discrete representations. These methods are limited in applying gradient-based techniques to optimize mesh geometry and topology. Since Mildenhall introduced the differentiable volumetric rendering technique to optimize a neural radiance field, a number of studies have been carried out to dive deeper into NeRF-based architecture. However, it is challenging for these methods to represent scenes with complex textures. Here is an example. NeRF, MIP-NeRF and August-NeRF can reconstruct the low-frequency geometry, but fail to generate high-quality fine details. Therefore, we propose a NeRF-based architecture to achieve the physically based spectral rendering. We construct the spectral radiance field for the scene information along the ray, which facilitates the rendering process and keeps the rendering pipeline simple yet effective by employing a physically based multi-spectral integral calculation for the L to XYZ to RGB conversion. Specifically, we embed the conversion matrix into the equation to calculate the CIE-XYZ values, and obtain a variant equation to generate the RGB spectrum maps. Then, calculating the variant equation in the form of summation to obtain the final RGB image of white illumination. Here shows an example that includes 11 RGB spectrum maps and 1 RGB image rendered with our hypothesis. Here is an overview of our pipeline. We first designed SpectralNeRF to construct the spectral radiance field and generate RGB spectrum maps with novel views using volume rendering. The color of the spectrum maps matches the distribution of the CIE color matching function. The SAU-net combines the discrete spectrum maps to produce high-quality RGB outputs. First, for a given ray origin and ray direction, we propose the SpectralNeRF to generate the spectral radiance and the density. Following NeRF, we use an 8-layer MLP and ReLU activation to predict the density, and following 2 fully connected layers to obtain the spectral radiance. Volume rendering is then applied to generate RGB spectrum maps with novel views. The color of the spectrum maps matches the distribution of the CIE color matching function. Then, the spectrum attention U-net, named SAU-net, is proposed to learn the correlations of spectrum maps and generate high-quality RGB outputs. Applying the SAU-net can imitate the original integral operation better and produce results close to the ground truth. Based on the U-net baseline, we first introduce the attention gate to refine features from the encoder. The high-level features before outputting to the next decoder stage are guided by the low-level features from the encoder using the attention mechanism. We further design a spectrum attention SA module to better explore the correlations of spectrum maps. Finally, the SAU-net generates high-quality RGB results with novel views. The spectral MLP involves spectral color transformations, and the SAU-net imitates integral operations for spectrum maps. The objective function includes the following two items. The first one is the spectral loss, which pushes the spectral MLP to produce desired spectrum maps. Similar to NeRF, we simultaneously optimize a coarse model and a fine model. The second one is the RGB reconstruction loss, which optimizes the SAU-net to generate high-quality RGB images. To validate our method, we render and capture various datasets. First, 4 scenes are designed without background and the viewpoints are captured on a sphere surrounding the models. Second, 4 scenes use texture to construct the walls and floors, and their viewpoints are sampled on the upper hemisphere. Third, we render 2 indoor forward-facing scenes with limited camera location and camera perspectives. The above datasets are all synthetic scenes. We further capture 4 forward-facing real datasets to validate the robustness of our method using a camera and 8 color absorbers. Here shows our experiments. We compare our method with recent NeRF-based methods on our datasets. Benefiting from the spectral radiance field, our method outperforms other methods because it simplifies complicated scenes. On average, our method achieves 5% improvements compared to other NeRF-based methods. Here are some qualitative results on synthetic datasets. Other methods can reconstruct the low-frequency geometry, but fail to generate high-quality fine details. Here are some qualitative results on real-world datasets. By concentrating on different spectral components of the complicated scene, our method outperforms the comparison methods by preserving more details. We also show several generated spectrum maps of the spectral MLP, which are similar to the ground truth. Computing efficiency is also an important factor for evaluating the view synthesis performance. The speed of our method is comparable to general NeRF methods, which is a little slower than NeRF, and the volume rendering spectrum maps takes most of the extra time. However, introducing the spectral radiance field with a little more computational time is advisable in exchange for significant improvement in performance. Here are ablation studies on several important components. First, as shown in rows A and B, introducing the spectral radiance fields can effectively improve the performance. Second, as shown in rows G and H, removing the attention gate, AG, will degrade the results. Third, rows C, D, E, and H, show the results when embedding the SA module to different encoder blocks. The SA module is placed in the first 2 encoders to best explore the correlations of spectrum maps. The SpectralNeRF can be considered as an improvement technique of existing NeRF-based methods, which can promote their performance if we apply their network architecture as the baseline of spectral MLP. We conduct the experiments when transferring the spectral radiance fields in SAU-net to August NeRF, named S-August NeRF, and improving the average PSNR score from 31.157 to 32.626. In summary, we propose SpectralNeRF, that builds up physically based rendering with NeRF from the spectral perspective, which leads to mutual enhancement of spectral rendering and NeRF-based methods. We designed the SAU-net to fuse the discrete spectrum maps to generate high-quality RGB images, which can approach the integral calculation in spectral rendering. We render spectral datasets and capture real-world scenes with spectrum maps and RGB images, and provide comprehensive comparisons of these datasets with several NeRF-based methods to demonstrate the superiority of the SpectralNeRF. Thank you.